We're going to move on now to study probability. Why? Because social research usually involves sampling of some kind. And probability is important because it allows us to determine how likely it is that the sample we analyze is representative of the population that we draw that sample from. So let's consider a normal six-sided die. What's the probability that we roll a 2? If you guessed that the probability of rolling a 2 was 1 over 6 or 1/6, then you're correct. The probability of rolling any face is 1/6. What's important to understand here is that we accounted for every possible outcome that could occur when we roll a fair six-sided die, and that all of these probabilities add up to 1. 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 equals 1. We can't have a probability of greater than 1, and we can't have a probability of less than 0. There's no such thing as a negative probability. Let's go over a couple of simple rules about probabilities. How about the probability of rolling a 1 or a 2 or a 4? Or probabilities follow what's called the addition rule. You add up the probability of each event independent of the others, and that gives you the probability of producing any outcome. Let's change things up a bit and consider a standard pack of cards. What's the probability of drawing a queen of diamonds from a standard pack of cards? Well, there are 52 cards in a standard deck, and there's only one queen of diamonds. So the probability of drawing a queen of diamonds is 1 over 52, or 0.0192. It's useful to know, by the way, that since there are 4 queens in a standard deck of cards, the probability of drawing any suit of a queen is 4 divided by 52. Okay, so we've drawn our queen of diamonds, and our deck now looks like this. What's the probability of drawing an ace of spades? Well, the probability of drawing an ace of spades, if we fail to return the queen of diamonds to the deck of cards, is now 1 over 51, since there are now only 51 cards in the deck. Of course, if we put the queen of diamonds back into the deck, then the probability of drawing an ace of spades is 1 over 52. Let's take a look at something called the multiplication rule. Determining the probability of 2 events occurring together follows what's called the multiplication rule. To find the probability of 2 events occurring, we have to multiply the probability of one event occurring by the probability of the other event occurring. I've done that in 2 ways here, once with replacement and once without replacement. You'll notice that the 2 probabilities differ by only 1/100,000th. For small samples drawn from relatively large populations, whether you replace or you don't replace doesn't make much of a practical difference. Probability is a vast field and a very interesting one, and also one that's very useful since it offers a method for dealing with uncertainty, which is a fundamental human concern. So what are some of the key takeaways from this discussion of probability that we've just seen? The first is that probabilities are always expressed as decimal percentages that range from 0 to +1. You cannot have a negative probability, and you can't have a probability that's greater than 1. This is by definition. The second is this idea that we've touched on but haven't really defined. It's the idea of random experiments. A random experiment is simply a trial or an event, the outcome of which cannot be predicted with certainty. Tossing a coin or selecting a card from a deck of cards are both examples of random experiments. The idea of a random experiment is important because it leads to the law of large numbers. The law of large numbers states that as the number of trials in a random experiment increases, the observed distribution of outcomes will approach the theoretically expected distribution of outcomes. We know theoretically, for example, that the probability of getting heads when we flip a coin is 0.5. If we flip a coin 4 times, we expect it to land on heads twice, but we wouldn't be surprised if it landed on heads, say, 3 times or even 4 times. In the case of 3 times, we compute the empirical probability of heads at 0.75. We'd be wrong, but the empirical probability is simply the outcome of the random experiment we conducted. If we flip the coin 1,000 times, we might well observe a run of 3 or 4, but if we tabulated all 1,000 outcomes, we'd see that they come very close to the expected result, which is seeing heads about half the time. This is an important idea for us here because it gets at the notion of sample size. The larger the sample size, the more likely it is that what we observe reflects what's actually happening in the real world. The underlying and fundamental question for this course is just that. To what extent is what we've observed in a sample reflective of what's happening out there in the real world? I hope you found this video helpful. I hope you found it interesting, and there'll be more to come.